So hello everyone. I'm happy to host Dan here. Dan Vilenchik is a senior lecturer at the School of Electrical and Computer Engineering in Ben-Gurion University. His research interests including both theoretical aspects of machine learning, mainly computational statistics, and hands-on machine learning, focusing on online social platform and text analysis. And today he will talk with us about the computational statistical trade-off in the problem of finding sparse principal components in high-dimensional data. So, Dan, the stage is yours.
Thank you for the introduction. Of course, you are welcome to ask questions during the talk and the discussions. And I really wanted to be in person, but yeah, the reality is sometimes stronger than our wishes. Okay, so so one typical setting in machine learning in statistics is the following pipeline. So we have some latent distribution with parameters theta, a vector of parameters, and they are latent. We don't know them. We just get samples. We see samples from them, and we'll use n to denote the number of samples and p the dimension of the distribution. So in many cases, we get this table of features, right? So the columns are the features and the rows are the samples. And then we have some task estimation. Maybe we want to estimate the parameter theta or some learning task. And in this pipeline, we care about two things. One is, of course, consistency. So we want the estimated parameters to converge or to be close in some norm to the real parameters theta. And we want the task to be carried out efficiently. Right? We don't want to wait 2 years to get this result. In many cases, we can get both, and that's very nice. But in some cases, some interesting cases, we cannot get both. And there is some trade-off between efficiency and consistency. And we'll see an example in this talk today. And the example comes from the problem of principal component analysis. So I'm pretty sure most of you are familiar with PCA, but just briefly for those who are not. So PCA is a very basic and widely used tool in statistics, in machine learning, especially when we have high-dimensional data. So here, for example, we have a 3-dimensional data. And if we want to project it on 2 dimensions, then we can choose 2 features, right? Let's say X and Y, the 2 axes, and project the data. But we can choose a more clever projection, and that's according to the directions of importance in the data, and that's the directions where the variance is maximized. And then the data is projected on those directions. And so the task is to find those interesting directions, the directions that maximize the variance, and to reduce. And the dimensionality reduction is used for many tasks, for visualization, noise reduction, to make things more efficient. So people use PCA a lot in practice. So how do we compute the PCs? How do we find those directions? So luckily, there's a closed form. It's very easy to compute them, at least the recipe. You estimate the covariance matrix. So X would be the table that I showed in the last slide. That's the formula for the covariance matrix if X is centered. And let's assume that. So sigma hat is the P by P covariance matrix, and then you just compute the composition of sigma hat. Right? So you write it as a sum of rank 1 matrices, where V1 is the leading eigenvector of sigma hat, and V2 is the second eigenvector, and those turn out to be the PCs. Right? So it's a 2-line calculation to see why V1, the leading eigenvector of sigma hat, is also the direction which maximizes the variance. That's a cute 1-line calculation. And then we just truncate. So we throw away the low value eigenvectors, and we stay with maybe 1 or 2, depending if you want visualization, and so on. So that's the problem, which again goes back to Pearson, 1901, and is heavily used across discipline. But the question is, okay, we want to visualize the data, right? So this sigma hat needs to be informative. We can always compute sigma hat, right? This is the computation, but the question is, does sigma hat really converge to sigma, the latent, the ground truth distribution? So here's an example, an interesting example from a paper of Leo Wolf and a co-author, Vilenchik, from 2005. And they, what you see here are two distributions, 203-dimensional distributions, and they are identically distributed on 200 dimensions. So 200 features are identically distributed between the two distributions, and 3 features have a different distribution. And here you see a plot of the 200 points on those 3 features, right? So these 3 features separate the 2 distributions, but the trick is that we don't know the 3 features. So suppose that we have this game and we want to know which 3 features are important. And I'll just jump to panel C. This is PCA on the leading 2 principal components. So we compute the covariance matrix, the pooled covariance matrix, we project the data, but we see that the separation disappears. The picture is smeared. We just see the 200 IID identically distributed dimensions take over, and those 3 separating dimensions are gone. We don't see them. Here we see PCA on the pooled 3x3 covariance matrix. Now, of course, the leading 2 PCs reflect the dimension, reflect this separation. So this picture here is in correspondence with the ground truth, with the 3 important features. Let's say that the signal lies in those 3 features. So this is in line with the signal. This is not in line with the signal. This is in line with the noise. And then in panel D, they recompute PCA, but not using this formula, this standard formula, but they use some other trick. They call it sparse PCA. So they use some other algorithm to compute. They will not be already the principal components. They are not eigenvectors of sigma hat, nor of sigma, but they compute 2 vectors which are informative. We see that this computation carried on a 203 by 203 covariance matrix regains consistency. So now this picture is consistent with the ground truth, with how the data should look like, if we were to choose the right 3 dimensions.
Dan, question?
Yeah, sure.
This isn't really about consistency. It's more about the fact that you could get the same counterexample even if sigma hat does exactly equal to sigma. It's just that the eigenvectors of sigma are not necessarily the informative ones, but it's not about sampling noise, right?
So but in this case, sigma, if the expectation is 0, so suppose that the 200 dimensions are normally distributed, like Wisher distribution with 0 covariance, then in sigma hat, you will have identity, zeros everywhere, and just a 3x3 matrix. So if you could obtain sigma, you would see this picture exactly. So it is about consistency in this case. So sometimes maybe not, but sometimes it's definitely about consistency. If
it could be that the principal that the informative features are not the ones that discriminate well, are not the ones that maximize the variance, even in infinite data. This is not it's very easy to construct examples like that. So right. That's not what's going on here?
Right. So that I would call the information limit. You're right. Sometimes the noise is so large that the informative features, you just cannot tell them. And that's another case. But
yeah, it's not even necessarily noise. Sometimes the features that are, that maximize the variance. So for example, suppose you're trying to discriminate between, I don't know, people with mustaches and people without mustaches. That could be a very small change variance feature, but it ends up being discriminative for the task that you want to do. So I think it's very easy to construct examples where it's not about consistency, but rather about the difference between the discriminative feature and the high variance feature.
Right. So in this case, so I'm talking about the easy case where they are both. The discriminative features are the one with the higher variance. But since you have many more non-discriminative features, just because you have many of them, they will overtake, even if their variance is lower.
Okay, got it.
Per feature. So that's the point. Otherwise, you're right. So then, in some sense, there's nothing you can do. But I'm talking here about an easier case where you can do. If you would run an exhaustive search on a 3x3 submatrices, you would nail it down. Okay. So that's the case. But here, I mean, if you just take the naive approach, it's bad news.
Okay.
And so I'm talking. So thanks for sharpening the point. So I'm talking about the case where consistency solves the problem. If you could get a consistent estimate of sigma, then you're good. But and this is the case in classical statistics, when the number of features is much smaller than the number of samples. Then as the number, so this is a CLT type result, as n grows to infinity, sufficiently large, then you are good and you can compute eigendecomposition of sigma hat. But in high dimensional setting, which is the focus of this talk, when P and N are comparable, let's say the same, you can think about them as the same, then the eigenvectors of sigma hat are uncorrelated or have a very low correlation with the eigenvectors of sigma. And then this naive computation gives you this picture because you're just projecting data on noise, on random directions in some sense, and then you will not, and then the chance that you will hit the right angle, the eigenvalue will hit this angle is very slim, right? Okay. So what can you do? Because people do care about computing, projecting high-dimensional data in biology, in genetics. People care about this problem. Therefore, people use regularization and introduced sparse PCA. So there are very many variants of sparse PCA. And also note that our goal is to, let's say that our goal is to estimate the leading PC or maybe the leading two PCs, not to estimate sigma, right? So that's an easier goal because we just want let's say the 2-3 main directions in the data, or even the leading PC, and then to from that to extract the relevant features. And one popular assumption is that a leading PC is k-sparse, and k-sparse meaning that it has few non-zero entries. So you can think of a genetic problem where you have 5,000 genes extracted, and maybe 5 out of the 5,000 genes are responsible for the disease. You just don't know which 5. But you know that let's say that the leading PC will be 5 sparse. You just don't know which 5 entries are missing, which 5 entries are non-zero, and that's the game that we are going to play. Okay, you assume that the vector is k-sparse. You just don't know which entries are the relevant one, which features are important and which are not, which are noise. Okay, so here is one popular estimator that people use for the leading PC. So this is just if we don't have this regularization part, this is just the leading eigenvalue of sigma hat, or the leading eigenvector of sigma hat. And here we have a regularization term, which is the L0 norm of V, just the number of non-zero entries in V. So you can compute sigma hat and then solve this formula, this optimization problem. And if you choose lambda, let's say correctly, the problem is consistent again. So PC1, the estimated PC1 is indeed what you want. And then if you solve this problem, you will get this picture. If you will project it, let's say, on the leading PC, the x-axis, you will see the blue and the red separated. And if you don't use a regularization and you project on this axis, you will see them blended together. Okay, but the problem is that this optimization problem is non-convex and therefore NP-hard. So you cannot naively solve this. You can naively solve this part, but that's in some cases, in high dimensional setting, that's useless. Sometimes it's not useless, right? We'll see. I mean, sometimes even in high dimension, this gives you a good approximation. This is enough, but sometimes it's not enough. And this is, and if you add this regularization, then you extend the range of parameters where you get a consistent estimator. And let's say that we are in the regime where the solution of this, and this is again to Yair's comment, let's say that we are in the regime of parameters, or our problem is such that the solution of this problem is unique, and it indeed coincides with the features of interest. Okay, because otherwise, if the features of interest are with very low variance, then in some sense, it's a different problem. Okay, so how to solve sparse PCA? So again, this is NP-hard. What do people do? They don't solve NP-hard problems. Of course, you can exhaustively search all K by K submatrices and just see which has the largest eigenvalue, which means explains the most variance. And this is maybe good when P and K are really small, but in many cases, P is large and K is large. So exhaustive search is not a good solution. And people use many polynomial time heuristics. What do we mean by a polynomial time heuristic? We mean an algorithm which is efficient, it runs fast, but it does not guarantee consistency. So sometimes it returns a good estimators, and sometimes it returns garbage. Here are some examples. The most naive one is called diagonal thresholding, and it was analyzed by Johnston and Liu many years ago. And what you do is you just take the features with largest variance. And it's called diagonal thresholding because they lie on the diagonal of the adjacency matrix, and you just take the K largest entries of the diagonal. And here is an example. Let's say every feature is a frequency, and then you say, oh, I have high energy in 4 features, and that would be my guess for the K non-zero entries. More sophisticated polynomial time heuristics involve relaxation of the search space. So instead of searching over a non-convex body, we change. So this L0 norm is replaced, let's say, with an L1 norm, and then the body becomes convex, and then you minimize, or in our case, you maximize the same function just over a larger set, and then you hope that the maximizer on the largest set falls inside the smaller set. So you get, or is close to the smaller set, and then you get, and then again, you get a consistent solution. And such relaxations, for example, semi-definite programming is used, or other spectral, so this is used as relaxation. Lasso, which is a regression, so you can recast PCA as a regression problem and then solve a regularized regression. So they are used to solve sparse PCA, and we'll discuss their performance later. But again, the problem is NP-hard. So all these heuristics work up to in a certain regime of parameters, and they must fail in another regime.
Dan?
Ken, yes.
If I can ask a question, just to make sure I understand, the whole thing that we're doing now is to find a sparse PCA because we want to avoid the complex computation of PCA in high dimension, right? Because...
And not only, if I want to understand, so suppose I just want to visualize the data to see sick and the healthy people. So if I compute PCA, I project, and I see no, everybody is the same. I want this picture. I want a picture that help me separate, I know. It's not just about efficiency, it's about analyzing the data.
But if we go back to the example you gave with the genes, so for instance, if you have 5,000 genes and only 3 are responsible, then if you do PCA at a high dimension, although it's a high cost, you should get still the separation, right? If there are actually 3 dimensions that are orthogonal and...
Yeah, but I don't know them. So this is what I will get if I might get if I just compute PCA in high dimensions, because the 200 dimensions are very noisy, and then the variance is maximized in their direction, just because there are many of them and they are very noisy.
Oh, I understand. So it's because of the noise, but if it was like a higher signal to noise, then you could just do regular PCA at a high dimension and polynomial time, it would work, right?
This is what, yeah. So depending on how high is the signal to noise ratio, exactly. So this leads us to this example here. So to this illustration. So it's all about the signal to noise ratio. When the SNR is very large, then, so in this regime, we get the accuracy of polynomial times, and in some cases even of naive PCA. You don't need to do even a relaxation. You just solve PCA, and it gives you the right solution, right? In large SNR, in high SNR. But then as the SNR decreases, then the polynomial time algorithms, including the naive PCA, deteriorate, and then the accuracy is non-existent. So let's say that the accuracy in this case is just hitting the right number, the right features. Okay, so we have, so let's say 1 to k is the right non-zero entries, and then this is the guess of the algorithm, and we want just to find what percentage of features it hit correctly. Okay, I'll skip that. Okay, and in many cases, or alternatively, we can ask for this picture, which is interesting also, but far less studied. We want the accuracy to be fixed. So we want the algorithm always to return 90% of the features of the support of the sparse eigenvector, but we allow the algorithm to increase the running time. So when the SNR is very high, so we want accuracy with low computational resources, but as the SNR decreases, we allow the algorithm to increase the running time, but we always want the algorithm to find the right solution. And this is the focus in this work. How can we do it in a non-trivial way? Can we increase frugally the running time so that we maintain consistency, maintain accuracy, and not just run exhaustive search, right? So we can say, okay, in this regime, when polynomial time algorithms fail, just run exhaustive search. Can we do something smarter, although non-polynomial? Just a second, I don't know, something is, just remove this. Got here, sorry for that. Okay. Okay, so I'll talk about a new design principle. For those from computer science, they know it as expected polynomial time, or I forgot, anytime algorithms. So it's called anytime algorithm. The algorithms that work always, but the computational resources that they invest depend on the problem. And so we want a framework that allows us to calibrate the running time with the SNR, with the computational resources, available time. Suppose you have 2 months until submission. So you started to work on your submission 2 months ahead, of course, a non-existing event. And then you want to spend the entire 2 months crunching your cluster that you bought to get the right solution. You don't care about solutions that take 1 minute to compute. And you are willing to spend a lot of time. Okay, so here's one naive way to fix, to solve the problem. You just run exhaustive search for 2 months, and then you go over all submatrices, k by k submatrices, and after 2 months, you preempt, you stop the computation, and you return the best solution that you got, the best matrix, the one that explains most variance. But as we will see in a second, we can do better than that. And the inspiration comes from the following very simple greedy algorithm for submodular optimization. So you can think of PCA, of sparse PCA, as the following problem. So you have a mapping between subsets of features and R. Every subset of feature, you can map it to the explained variance on the submatrix, k by k submatrix, let's say k by k submatrix, induced by those features. So that's the mapping. And in this language, we just want to find the maximizer, the maximal solution, the maximizer S of size k of this function. And it turns out that this exact formulation was studied quite extensively, and especially for submodular functions. So just briefly, a function in our case is submodular if for every S prime subset of S. So if you add a feature X to S, then you gain less if S is larger. So you gain more from adding features, you gain more in the variance from adding features to smaller sets. So this makes sense, right? Because as you have more features, then any additional feature can just explain less variance. And monotonicity, more features explain more variance. Okay, so just intuitively, F is our F here is submodular, and here is a greedy algorithm that guarantees some approximation of the optimal solution. So we'll see the guarantee. So here's the algorithm. What you would think, you start with an empty set of features, and then you just add the feature that maximizes the variance. The variance with the that maximizes the variance in the direction of the already collected features. Right? So you just add the features one by one greedily, and then you stop when you hit K features. Now we augmented this algorithm in the following way. You don't start with an empty set. You start with a seed of size K star, which is some number smaller than K, and then you add the remaining features. And we'll see that this is crucial. I mean, you cannot start, in some cases, maybe you can start with an empty set, but in low SNR regimes, this is what gives you the ability to recover the signal accurately. And as you can imagine, okay, I'll get to it in a second. Okay, so that's the augmentation that you can think for this algorithm. Of course, you have to somehow pick the seed. So it's of size K star, which is some parameter smaller than K, smaller or equal than K, and then you have to choose the right seed. So this is the algorithm that this is our variant of this algorithm. What you see here is just the greedy algorithm. It gets a seed, and then it completes the seed greedily to a suggested solution S by maximizing some function. Of course, the function could be this function or any other function that you want. But we wrap this greedy algorithm with an exhaustive search over all possible seeds of size K star. So instead of running an exhaustive search on all K by K submatrices, we run an exhaustive search on all possible seeds for this simple greedy algorithm. And then every seed we complete according to this scheme. And eventually we choose the best seed. Okay, so so here is for illustration one iteration of exhaustive search. You have a seed S, so that should be S star. So you have a seed S, and then you inspect various features that you want to add to S, and then you discover that X is better in this cost function F1, and then you just add X instead of C. For the sake of the analysis, we chose here the variance, which is what you want to choose. You want eventually the K features that explain the most variance. And here we didn't choose the variance, but for analysis, we chose, and also for simulation, it gave the same result. We chose a slightly different function, and that's the average covariance. So we add the variable that has the largest average covariance with the already existing features. And you can add them in bulk. So you add the K minus K star variables together, or you can add them one by one. There are two variants of the algorithms. And again, simulation showed that there is no difference. But for the analysis in the paper, we added them in bulk. Again, if you want a nice, I think it's a nice warm-up question. If you like this kind of stuff, replace this with lambda 1 and replace this with a one-by-one analysis. Okay. So as I said, if you have no seed, you get this guarantee for the approximation of the optimal solution, 1 minus 1 over E. But this guarantee is useless in our case, or in many cases. It has to be useless in some sense, right? Because this gives you a polynomial time algorithm, so it cannot work all the time. But to see why this guarantee is useless and you have to use a seed, again, think of a Wishart distribution. So X is just normally distributed with expectation 0. So X is normally distributed with a covariance matrix the identity. right? So if you take the Wishart distribution and you take a random or just any k by k submatrix of that distribution, again, it's a Wishart distribution, and then that would be the value of the optimal solution. That would be lambda 1, the leading eigenvalue, which in our case, if n is much larger than k, is roughly 1. Right? So if you just take a random solution in this large matrix, so again, we have a p by p matrix. There is some area k by k, which is our interest, but we don't know it. So if we just guess a random solution, probably it will be just noise. And then the optimal solution, the solution in that k by k, in that k by k matrix is roughly 1. However, if we look at the right k by k solution, then there is some energy beta in those features, meaning that the leading eigenvalue is 1 plus beta for some beta larger than 0, fixed beta, let's say. So the guarantee, so that would be, let's say, the optimal solution over all k by k submatrices. This is what you get for a random k by k matrix. And this is much smaller than 1, right? So the guarantee, I mean, unless and this is what I think Guy asked. So if the SNR is really large, if beta is really large in the sense that this is larger than this, then you might expect even a trivial PCA, naive PCA to work. But in the cases where beta is rather small, and not too small, right? Here you have 0.67, so you can do the math. But in the case where beta is fixed but rather small, then this result gives you a useless guarantee, because the guarantee from greedy without a seed is even smaller than just guessing a random solution. Okay, so we have to have the seed, right? At some point, if the SNR is sufficient, is small, then without a seed, so that's the conclusion, without a seed, you just get garbage, or you're not guaranteed to get anything better than a random solution. So for the analysis part, so now let's talk about the analysis. I'm not going to get into the details of the proof. It's all in the paper. But note that our algorithm is actually a hierarchy of algorithms, and it's parameterized by this seed k star. So it interpolates between k star equals 0, which is diagonal thresholding, because you just take the k features with, I mean, you have no seed. So you just take the k features with largest variance. And at the other end, if you take k star to be k, that's just exhaustive search. So you have a family of algorithms with increasing computational effort. So the running time scales exponentially with k star. That's the running time. So you have a hierarchy of algorithms, which you can calibrate according to the SNR. And you're in the polynomial time regime when k star equals is constant, but super polynomial as you increase it. And this algorithm, when we ran it in simulation, of course, it's very easy to parallelize it and to run it in a distributed manner. And the rigorous analysis was carried out in the spiked covariance model. That's a very nice toy model introduced by Johnston in 2001. And this is the way the distribution is defined. So you have a planted solution, V star, and let's assume now that for simplicity that that's the signal that you're looking for. That's the sparse PC. And let's assume that it contains k non-zero entries just in the first k entries, and they are all the same. So all eigenvectors are normalized, so are unit vectors. So that's the spike, and we plant it in noise. What do we mean noise? So that's the population covariance matrix. This is the latent sigma that we don't know. So we have identity, which is just the Wishart distribution, or white noise, white Gaussian noise. And we have a rank 1 perturbation of this identity matrix. So that's a rank 1 matrix, V star transpose V, and beta is the beta and k together control the signal. So beta is some positive number. So the leading eigenvalue of this matrix, sigma, is 1 plus beta for V star and 1 for the remaining eigenvectors. So V star has eigenvalue 1 plus beta. All the remaining eigenvectors have eigenvalue 1. So in this case, going back to Yair's question, if I know sigma, so I know this structure, then immediately I know, just by looking at the non-zero entries of sigma, I know the solution. But I don't get sigma, I get X, a sample for sigma, and then depending on beta and depending on K, which determine the SNR together, then this defines the regime. Okay, in what regime of SNR do polynomial time heuristics work, fail, and we'll see it in a second. And I just mentioned then similar algorithmic ideas were published in parallel by Dean, Quinsky, Wine, Bandiera. In general, this problem of sparse PCA is widely studied in this community from various angles. And another nice thing to remember is that the planted click problem is very similar in nature to the planted spike or sparse PCA problem, right? So in the planted click model, you have a random graph, Erdos-Renyi G and half, and inside it, you plant a click of size K. So that would be, again, the spike, the click, the coordinates of the click, which is very similar to the coordinates of the features. That would be the adjacency matrix in the planted click model. So you have the Bernoulli 0-1 matrix, and then you have the rank 1 matrix, the click. And in our case, we have, instead of Bernoulli, a Wisher distribution, and then we add the spike, the rank 1 matrix to that. So the problems are very similar. Here you get a graph with a unusually dense small click. Here we have a Wishart matrix with an unusually dense submatrix. And in both cases, you need to find the needle in the haystack. So philosophically, both problems are very similar. And as we will see, those of you who are familiar with the planted click problem will see in the next slide or two, the same picture emerging, or in the sense that when do computationally efficient algorithms work, when do they fail? But still the PCA problem is harder. And I'll get to that at the end with a really nice open problem. Okay, so as for the analysis of our algorithm, so there are two properties that are sufficient for the success of this seed guided exhaustive search. The first one, I call it spectral separation. And it means the following. So let's say that this yellow part is the right. So this is the right solution that we are looking for. And if we have two candidate solutions, I and J, and the intersection of I with the planted solution is larger than the intersection of J, then the variance explained by the submatrix indexed by I is larger than the variance explained by the submatrix indexed by J. Namely, a greedy algorithm that just wants to maximize variance will drift towards this solution if he sees this progress of solutions. So this is one condition. The other condition is what I call golden seeds, and that's the fact that there exists a seed of size K star, which would be, of course, a subset of the right solution that you can extend to the right solution. So it's not clear that even if your seed, because you run over all possible seeds of size K star, so you get seeds here and here and here, at some point you will hit a seed inside the right set of features. Still, it is not clear that some variable outside the set of relevant features will be added to this purple thing by the greedy step. So the fact that the greedy step grows the solution almost entirely inside the yellow shape, the yellow part, this is again not necessarily the case, but if the seed is sufficiently large, that would be the case. So those are the two conditions. And then for the analysis, you want to understand when, under what SNR, in what regime of parameters of N, P, K, and beta. namely in what SNR regime those two conditions hold. Now, there are sufficient conditions, but in the other paper I mentioned, they show that in some sense those conditions are also necessary. So this analysis is tight. So as you said, how does the analysis go from bird's eye view? So you fix some seed, initial seed, and you look at the seed inside the support of the right size. Now, there are two competing processes. On the one hand, as you increase the seed, the probability of adding an erroneous feature to the seed for every seed decreases, right? Because the seed is like an attractor, it's like a magnet. Due to this model, the single spike model, but in general, you expect that features that are part of the signal to have a larger covariance between themselves compared to other features. Now, as the magnet grows, then its probability of attracting wrong features, noise features, decreases. On the other hand, as you increase the seed, you increase the running time. And then you want to find the balance, the minimal K star that allows correct reconstruction, because we want the accuracy has to be 1 or 1 minus epsilon, right? Because in this paradigm, we always want to succeed. And then this is the number, we'll see it in a second graphically, right? So again, some lower bound. So K star has to grow proportionally to K, to N, to beta. So here, again, I assume that P and N are the same. So it has to grow proportionally to these parameters, and it's better to see it graphically. Okay, so let's assume, so let's see the complexity map, how things look. So just for simplicity, let's assume that N equals P, and let's assume that beta is fixed, is 1/2, for example. And then only K governs the SNR. In what sense? If we go back to this picture, the smaller the click or the larger this area here, the easier the problem. So here, in this problem, the larger K, the harder the problem, because then the signal is smeared over more entries. So this submatrix is larger, but the red is closer to blue, right? Because this is a unit vector. So the more entries, the more features you have, then the more the signal is smeared over the entries, again, in this model, and the problem is harder. Of course, this should be beta, right? Now, of course, beta is also can compensate for that, but but to understand the principle behind it, we assume this is fixed and only K governs it. And similarly, in the planted click, as you increase K, you increase the signal, right? Because the unusually dense subgraph is larger, so it's more visible. So they operate inversely. In planted click, the larger K, the easier the problem. In PCA, the larger K, the harder the problem. Okay, so this axis here, K, is governs the SNR, and this is the accuracy. And now let's see what's known. So one result, Amini Wainwright, 2009, says that there's an information limit occurring at, everything here is theta of, I'm neglecting constants, at n over log p. So K, if n equals p, K is at the maximum p, the number of features. So very close to the maximum number of relevant features that you can imagine. There's an information limit, namely every algorithm, regardless of the running time, cannot obtain accuracy 1. So let's say we'll miss at least half of the entries. And complementing those results, showing that the naive exhaustive search actually recovers this planted spike up to the information limit. So this is one thing. Another thing is a computational phase transition, which means that polynomial time algorithms, which were analyzed in the single spike model, the diagonal thresholding, that's the simple greedy algorithm, spectral algorithms, semi-definite program relaxation, the lasso, all of them were analyzed up to this SNR regime, k equals square root n, or on the order of square root n. And beyond this regime, no polynomial time algorithm is known to succeed. And this phase transition is tight under the planted click hardness. And these are results of Bertet and Rigoulet and Bressler and Brennan. This is called 2019, showing that if you believe the planted click hardness problem, meaning that you cannot polynomially recover a click of size smaller than square root n, or asymptotically smaller than square root n in polynomial time, then if this under this assumption, then no polynomial time algorithm can recover the spike when k crosses square root n. So now for our results, so if you take seed of size 0, and that's exactly diagonal thresholding, this is a polynomial time algorithm, and it's so simple that it doesn't even hit the threshold. It goes square root log p shy of the threshold. And then if you want to get to the computational threshold, you need a more sophisticated algorithm, so that spectral algorithm or semi-definite programming both get to the computational threshold. And for our algorithm, you need to take a seed of size log n, meaning a pseudo-polynomial time. So that's for the easy regime, let's say the large high SNR regime. Now, but in simulations, this log n turned out to be 1, and we'll see it in a second, even for large instances. Now, the interesting part in this work, as we said, is what happens in the low SNR regime. So low SNR, we can parameterize it by k equals n to the half plus some epsilon. And then if you go back to the formula that I showed in the previous slide, then the scaling of the seed is like this, n to the 2 epsilon times log n. And again, probably this is this is tight, you cannot do better, which means that the running time scales exponentially with this, right? So this is k over square root n square rather than k. But this is much smaller than this, right? So it's exponential in n to the 2 epsilon rather than n to the half plus epsilon. But half plus epsilon is much larger than 2 epsilon for almost up to the information threshold. So you get something which is way better than exhaustive search. And if we look at it from this even more bird's eye view angle, so we have so in this problem of sparse PCA, but again, this picture recurs in planted click and in other problems. You have this strong SNR regime, which again, you can break it into very strong SNR and strong SNR. In the very strong SNR regime, really simple, naive, greedy algorithms work, like diagonal thresholding. And then if you want to get to the threshold of polynomial time algorithms, then you have to do something more clever, like SDP or spectral algorithms. And then there's a threshold where, regardless of how smart you are, polynomial time algorithms fail, and then you need to do something non-efficient. And in this work, we showed that you can do something non-efficient, but still reasonable. We'll see simulations, still something that you can program on a cluster, you can run it and get results. That's the weak SNR regime. But what's nice is that you have one algorithm that goes throughout. I mean, you don't have to change the algorithm. You just need to change the size of the seed. And that's a nice thing, that you have one paradigm that solves the entire regime, at least in this spiked covariance model, right? So this is everything about the spiked covariance model. But that was also something nice. Okay, some simulation. So we ran our algorithm in the spiked covariance model. We took n equals p equals 1,000. So you have 1,000 variables and 1,000 samples. You have 8 relevant features, and we fixed beta to be 1/2. Now here you have on the left, the first 3 algorithms are let's say, state-of-the-art, those two, state-of-the-art, also SDP, but covariance thresholding was proven by Montanari and Deshpande to be to get up to the information threshold with the best constant. So this is, let's say, the state-of-the-art algorithm, at least if you go by the theoretical analysis in the spiked covariance model. And we chose the parameters so we are in or slightly above the computational threshold. So this algorithm fails. What you see here is the mean accuracy and the median accuracy over 50 executions. So we sample the distribution, we run the algorithms, we ask them for the K features that they think are the right 8 features, we just compute their accuracy. So diagonal thresholding, that's the basic algorithm, take the 8 features with largest variance, fails miserably. This is like guessing, right? So this is like roughly, well, not like guessing, but again, it fails miserably. And then this is Lars, this is the regression algorithm, the one that solves regularized regression. This is covariance thresholding. As you can see, they run very fast, and this is only on a single processor. They run very fast, but give useless results. This is our algorithm, which is run on 90 cores. So the time that you see here, for example, 3 hours, it's 3 parallel hours. So it's something, so it's not 270, but maybe slightly less, but it's something like 270 hours on a single processor. So we see here, this is K star equals 1, the polynomial time regime, roughly the same result. And we see that as we increase the seed, we get, of course, the running time increases, but the accuracy increases correspondingly. So this is the anytime paradigm that you see here. You increase the running time and you increase the accuracy. Now the running time increases very fast, right? You increase K because it's exponential. So K star equals 4 perhaps can detect 90% of the spike running for a week. It's okay. And here is exhaustive search, which we allowed exactly the same 3 hours on 90 cores. But what we do here, we just randomly guess solutions of size K by K, and we save the one that explained the majority of the variance, and we compute the accuracy. So you can see that, again, if you have, let's say, 3 hours, then it's better to guess smaller solutions and extend them greedily than to guess larger solutions. So that's another algorithmic message from this picture. Okay, so now concluding remarks, and I think some nice open problem related to this sparse PCA thing. So what we saw here, that high dimensional data poses very interesting algorithmic versus statistical challenges. And traditional approaches, computer science approaches that split the world into efficient algorithms versus non-efficient algorithms, sometimes this dichotomy is too crude. And if you allow for a continuum, then you can get better results, perhaps also in practice. This would be nice to check, especially when you have enormous computational resources. Then settling for efficient algorithms that run fast and return, in some cases, garbage is limiting. And so this anytime paradigm is interesting. So algorithms that can take advantage of huge amounts of compute powers. And as we saw also in this easy regime, we got better results. So just using this paradigm and giving a small seed, so this is, we didn't prove it formally, but simulation showed that you get better results than the best algorithm that was designed with polynomial time in head. So if you just stick to polynomial time design principles, perhaps you're also limiting yourself from better algorithms. Another thing which is interesting is that practitioners actually don't use sparse PCA. So I searched many journals, scientific journals like Cell, Science, especially biology, biology applications from genetics. And they, if they use sparse PCA, they use diagonal thresholding, or they use some really naive techniques like computing the leading principal component and taking the k largest entries in that vector. And somehow it works, right? I mean, they don't use sparse PCA, perhaps because it works, the SNR is really large. And also, perhaps they could get better results if they used semi-definite programming, spectral algorithms, but somehow they don't use it. So these really nice theoretical results don't spill over to practitioners. They have many tunable parameters, and the analysis is asymptotic, so maybe it's less appealing. There are other alternatives other than PCA. If you want visualization, you can use, for example, t-SNE. And again, I think it's interesting to understand when this picture of computational threshold corresponds to actual data. Give examples of actual data sets where polynomial time algorithms fail. And it's not something that I saw, that I've seen people do. I think that one possible, I mean, if you design white box and simple algorithms, they may be more appealing to practitioners. So as the SNR drops, or as the problem gets more complicated, you can increase the sophistication of the algorithm, diagonal thresholding, lasso, covariance thresholding, SDP, so increase, or you can use a simple greedy algorithm and just slightly increase the running time. So maybe this kind of research where you want to stick to the simplest possible algorithm, but perhaps pay with running time, as we've seen in this in our greedy algorithm, or also in the when efficient algorithms are available, you still have to use pseudo polynomial time. Okay, so that's another interesting line of research. What happens when you restrict yourself to the basic algorithms? Can you still do interesting things? And I think that a very nice, interesting question would be the following collapse of the algorithmic hierarchy. So currently, the view is the following. As the SNR increase, so most researchers look at this regime, right? Where polynomial time algorithms work. And then there's this race also in planted click, also in sparse PCA, there's a race to get the best constant on the best efficient algorithm. And this is, so a series of results show, for example, which as I said, diagonal thresholding. So if you're really naive greedy, then asymptotically you suffer, right? So this algorithm will not get you accuracy up to the threshold, but slightly before. Then you can do covariance thresholding, which is a spectral algorithm, first introduced by Bickel and Levina, then analyzed by Deshpande and Montanari, where they show that it is asymptotically gives better result than diagonal thresholding. And then on top of it, you can use semi-definite programming, which is yet another generalization of this spectral technique. So it seems like as you take more and more sophisticated algorithms, you do better in terms of SNR. But I think that this picture is wrong, because in the planted click, I mean, it's wrong in some sense. In the planted click problem, there was a very interesting reverse greedy algorithm introduced by Uri Feige and Dan Aron, which showed, and they showed that this reverse greedy works exactly the same as semi-definite programming, spectral algorithm. Next slide, I'll just give it a brief and then I'm finished. So this very simple algorithm performs as well as very sophisticated, very non-appealing to practitioner algorithms, and then analyzed it. And they showed that in planted click, it hits the square root n threshold. So there is no real algorithmic hierarchy of more and more sophisticated algorithm reaching better and better results, unless maybe you're interested in the constant before the square root n. So in that sense, right? But if you're looking in general, then a simple greedy algorithm performs as well as SDP, again, in this under some assumptions. So I think this is a very interesting problem. In the sparse PCA problem, this was not shown. So there's a reverse greedy parallel to the reverse greedy of the planted click. I think analyzing this algorithm, which in simulation I saw that gave exactly the same results as SDP, as spectral theory, but the analysis is complicated in PCA. So it's more complicated in the planted spike in sparse PCA than in planted click. So if anyone is interested, I'll be happy to talk. And also, perhaps this hierarchy is true, but then you need some other models, not simple random models, but semi-random models. So if, for example, you don't take a random graph with a planted click, but you take a random graph, a planted click, and then some adversary can add edges or remove edges, maybe in that case, SDP is resilient to the adversary's actions, but simple greedy algorithms are not. So maybe there is a hierarchy of more and more sophisticated algorithms, but it will be interesting to justify this hierarchy, for example, in using semi-random models. And this was done already maybe 20 years ago in various other problems like planted coloring, planted SAT, planted click. So it was shown that SDP is more robust than spectral algorithm. Again, showing this in sparse PCA, I think it's a very interesting open problem because the analysis is more challenging because it's not like GNP where edges are independent. Here you have dependency. The random processes are more complicated to analyze. So I think it's a really nice a host of open problems if somebody is interested. Thanks. Questions, remarks?
לי יש שאלה, רשמתי אותה בצ'אט כדי לא לשכוח אותה.
לא הסתכלתי על הצ'אט.
אוקיי. המלג שלה זה למה לא פשוט אוטו-אנקודר, כאילו למה אנחנו טורחים לדבר על מודלים ליניאריים כמו PCA.
אז קודם כל ספרס PCA, מודלים ליניאריים, הכוונה הטלה על מרחב.
כן, למצוא את מקודם עשינו הכנה כזה עם המטריצה A ו-B, כפל מטריצות זה משהו ליניארי, כאילו כשאנחנו מדברים על אוטו-אנקודרים אנחנו מכניסים שכבות של אקטיבציה ששוברות את הליניאריות, או רליו ודברים קלאסיים אחרים.
אז א', אני חושב שזה דבר סופר, אז השאלה עיקרית, קודם כל יש את השאלה הפרקטית והשאלה התיאורטית. אתה מדבר מבחינה תיאורטית או מבחינה, נגיד, למה מדען ביולוג גנטיקאי לא ישתמש באוטו-אנקודר בשביל לעשות פיצ'ר סלקשן? זו השאלה?
כן.
אז א', אני לא גנטיקאי, אז אין לי תשובה. יכול להיות שהם כבר אולי חלקם עושים את זה, אבל קודם כל PCA משמש לויזואליזציה גם, לא רק לפיצ'ר סלקשן. כלומר, אתה באמת מקבל, זה explainable. אתה יודע מה אתה עושה, אתה מחשב PCA, אתה לא סתם מקבל מרחב, אתה מקבל את הצירים המרכזיים בדאטה, אם יש לך דאטה רב-מימדי, אתה מוריד אותו למימד נמוך, אתה יכול לראות, אתה יכול לעשות interpretation, עבור practitioners זה priceless, הדברים האלה, הם רוצים את זה, לא מעניין אותם פרדיקציה רק של עצמה, הם רוצים להבין למה. מבחינת תיאוריה, אני חושב שזו שאלה מצוינת, הנה, תוכיח אימון של אוטו-אנקודר ברג'ים הזה מתכנס. כן, מתכנס במובן באיזשהו מובן שזה נותן את הכניסות הנכונות, ואפילו אם זה מעניין להוכיח, אפשר להתחיל ב-very easy regime. האזור הזה שבו הדבר הכי שטותי של לקחת את K, או הכי טריוויאלי של לקחת את K הכניסות עם הווריאנס הכי גדול, פותר. האם אוטו-אנקודר מתכנס גם שם? שוב, אפשר לבדוק את זה בסימולציה, אחר כך בהוכחה. יש פה הרבה שאלות.
Any more questions from the audience?
טוב.
Okay, so thank you, Dan, for this great talk.
אוקיי, תודה, ואם מישהו אחר כך רוצה אופליין, לשלוח לי מייל, מעניין אותו לעבוד על הדברים האלה, בשמחה.
תודה רבה.
להתראות.
ביי ביי.
ביי ביי.